Yeah, thank you very much, Jürgen. So yeah, again, thank you for attending my talk. It's a bit awkward to be online again, but I hope I can entertain you with this topic on the tipping of the Atlantic Ocean circulation. Now, this is work funded by, in this case, by the European Research Council and also by a training network from the EU, which is called Critical Earth. And I'm doing this work at the moment with several people, which are listed below. Some of it are my PhDs or postdocs, some are collaborators. The topic is about okay. If you look at, say, a typical, say, picture of the ocean circulation, so this is from a model simulation, but also observation assimilated into it. So it's called, we call it a reanalysis product. And here you get a glimpse of, say, the ocean circulation, where you see the streamlines here in white, and you see the Gulf Stream in the North Atlantic. And the impression you get is that it's, this is a multi-scale flow, varying on many time scales, with a lot of instabilities appearing. Here we zoom into the Agulhas current, where you see that there's a mean current which retroflects into the Southern Ocean near South Africa, but then also you see all kind of rings formation which move in the Indian Ocean. And so within this whole, say, multi-scale flow, which is currently looking like as you see here, there's a problem. And the problem is that and this is really well worded into one of the papers in the Washington Post in last August and in 2021. And it says here, a critical ocean system may be heading for collapse due to climate change. Now, the particular study here is from my colleague Nicholas Boers, who looked at observations and find indications that, there's a collapse of a certain part of the ocean circulation. And this is where the story is about today. So first we're going to look at what is this Atlantic Meridional overturning circulation. And well, what you see here is a cartoon of this circulation, where you see the red currents going northwards, taking heat northwards, and then what happens is they cool in the north, and then you get a return current, and you get a deep current below the Gulf Stream southwards. Now, if you look at, say, the zonally average circulation, so you integrate this flow over the zonal direction, so from America to Africa, then you can define a stream function in the meridional vertical plane. You see that to the right here. So latitude is on the x-axis, depth on the y-axis, and the stream function gives you a zonally averaged volume transport. And between, say, this maximum here, which we call the AMOC strength, and the surface here, you see that in this case is about, say, 20 swerdrups going northward, and one swerdup is about 10 Amazon rivers, to give an idea. Now here, you see this is not, we cannot observe this is from a model, but what we can observe is these data. So there's several instruments into the North Atlantic water, and the earliest one to move in was the rapid array, which is at 26 north. And if you look at the right picture to the top, where you see the AMOC strength, so this is this maximum of the overturning stream function versus time. And then the red curve here gives you the, say, annual values. The thin red curve and the thick red curve will give you the sort of a long-term average over 5 years, so the 5-year running mean. And then you see that, well, we don't know so much about the AMOC strength. We have about, say, well, 20-year time series, a little less than that. And we see that it's highly fluctuating, and that also, it decreased over the period 2004 to 2014, but then now it sort of recovers, not to the original strength, but say a bit in that direction. Now, there's also other instruments in the water, like OSNAP, which is the orange curves, which you see in the bottom and middle panel. And there you see that, well, we now don't know much. There's now a new data set where we have about 6 years of OSNAP, and that's really too short to look at long-term changes of this AMOC in the north part of the Atlantic. Now, why is the AMOC, why is it heading for collapse? Well, to sketch that, let's look at the situation in the North Atlantic, where you have heat input in the equatorial zone and heat output at the polar zone. And you know it's very hot also there, so there's a lot of evaporation in this equatorial part. So it's fresh water going out, and in the northern polar part is fresh water going in. Then if you would look at the circulation, which would result from density differences, pure due to temperature, then you would expect, here heat is going out here, so it's cooler in the north. So you would expect the water to sink there and then make a return circuit, say at depth. Now, this is actually the type of circulation we see in the observations. But you could also imagine that, suppose it's pure salinity driven, then you would have fresh water going out here. So it would be salty in this, say, equatorial part. And then the density would be higher here, and you would expect this type of circulation. So you see in this, the main point here, that temperature and salinity, they have opposing contributions to the AMOC. And so they work against each other. Now, the first one to realize that could lead to, say, special phenomena was Henry Stommel. And he devised a model just due to two boxes, particularly, tuned to that picture I showed in the previous slide. So you have an equatorial box, you have a polar box, there's a flow, the AMOC set up by the density difference. So if the polar density difference is bigger than the equatorial one, you get the circulation, which is sketched here in the red arrows. You have an exchange of fresh water and heat at the surface. And just show you the equations, very simple balances of heat and salt over the boxes. And the particular thing is, if you non-dimensionalize this and you look at a picture where the freshwater forcing is on the x-axis, now this is dimensionless, and the AMOC strength is at the vertical axis, this is also dimensionless, then what you see is that, and this was very peculiar at that time, that you actually have a region in freshwater forcing where you have two states which are stable. So this is a typical bifurcation diagram where you have steady states as function of a parameter. So these are all steady states of that model. Now, so between this L1 and L2, which are two solenoid bifurcations, you have this region of multiple states, and you have an AMOC which has a circulation downward with downwelling in the pole and downwelling at the equator. So that's exactly these two limits which you can imagine when it's pure thermal or pure salinity driven. So this is the model. Now, why is that? What's the mechanism of how can you go from one state to the other? Well, you have, suppose you have this thermally driven circulation, and now you put the background state here, which is warm and salty here and cold and fresh in the north. If you put a freshwater anomaly there, then it will decrease the density here. So the circulation is weakened. Now this will lead to a decreased heat transport northward. So that would increase the density. So that's a negative feedback. But it would also lead to decreased salt transport northward. And that would amplify this perturbation. Now, which of those wins depends on the interaction with the atmosphere. Now, there's no damping of salinity anomalies. Precipitation is not influenced by ocean salinity, but the heat anomalies are damped relatively quickly. And so what happens is that the salinity anomaly can, undisturbed propagate northward, amplify this perturbation, and you get a positive feedback, which spins down this AMOC. So that's the mechanism. You would assume, well, you only need a meridional velocity perturbation due to a freshwater perturbation. So it should also be pretty robust. Now, let's look at, the model hierarchy. There's a whole model hierarchy where you can study this problem. It starts with Stommel, which we call box models. So here we see the other box models, which are particularly designed for certain aspects of the problem. And when you look at the dimension of the dynamical system, so that is the number of unknowns in the in the equations, then you sort of are up to 10 or so. There's some more extensive ones, but that's sort of the order of magnitude. And then we go up, we have, one-dimensional spatially models. There are two-dimensional models where you look at the vertical depth. You can imagine that you have to sort of parameterize rotation in these models, the effect of the Earth rotation. Then there's a whole hierarchy of models which are three-dimensional, but where you can study effects of geometry and basin, double basins, and eventually you end up with some ocean-only model where you have, the full ocean models set up, but with a very simple atmosphere coupling. And then we have, of course, the modern climate models. And well, these are usually referred to as CMIP, right? This comes from the model intercomparison projects. And the latest one is number 6. We're now up to number 7. But those are substantially, well, very high dimensional models where you get into, 10 billion degrees of freedom or more. Now, what do these models can tell you? Well, they can tell you the impacts of this, say, weakening of the AMOC. And this is quite a recent study in Nature Climate Change where they basically put fresh water in the northern North Atlantic, so in this region here, and then looked at the decrease of the AMOC, and then looked at, say, over the last 50 years of this simulation, so it's time, and you see the transport, which is the AMOC strength here, and the black is the control, and the red is where the AMOC is weakened. And when you look at this surface temperature differences between this weakened state and the, say, the control state, you see that there's really quite some impact in terms of here in the northern North Atlantic, also other regions, but particularly in the north, where you see anomalies up to -10, -15 degrees. There are also quite some changes in precipitation. And so this is quite an impactful event if this had happened. And this is important. So what do we like to know? Well, in this model hierarchy, we'd like to know, is the present day AMOC, is it in a multi-stable regime, right, with a strong or weak state? And this is important to know. And the second question is, if that's the case, so if it is in this multi-stable regime, what's the probability that you get a transition before the year 2100 on the climate change? Now I go through both questions and see how far we are in that. For the first question, we go actually into the model hierarchy. We take one of those models here. This is a model which is still ocean only. It has about, say, 100,000 degrees of freedom. And the advantage of what you can do with that is that you can actually do numerical bifurcation analysis. Just as you would do for the Stommel model, which has 2 degrees of freedom, you can do that also for these higher dimensional models. And well, that has been done. And so what you do, you take this full-blown ocean model. It's quite low resolution. And what you do is that you add fresh water here with a sort of strength here, gamma P. So 0.1 would be here about 1 Amazon River. And you look at the steady states of this model. So the full ocean circulation flow, 3-dimensional, and also the AMOC versus this parameter gamma P. And then you see that, you see the strength is a little weak here because the model, because of its resolution, is more viscous than, say, you would like. But here you see that there's a bifurcation diagram which looks, fairly similar to the Stommel model, even if this is much more higher dimensional. And it's also this overlap region here of multiple states. It's controlled by these 2 saddle node bifurcations, L+ and L-. Now, the problem we have now is, in present day, suppose that this actually would hold. Of course, it's much too simple probably, but suppose it would hold. Then you would like to know whether you're here, right, in this single equilibrium regime or in this multiple equilibrium regime. Of course, many people focus on this point here. When if you vary this gamma P, you would actually jump off and go to this collapsed state here. But it's much more important to know whether you've crossed this point B here. And so how do you do that? Well, you have to look at integral balances because, saddle nodes are always associated with some balance breaking and usually in integral balances, because there's no existence of nearby solutions. And so you want to know what characterizes physically this point here, B. Now, the advantage of calculating bifurcation diagrams is that you can also look at all kinds of physical quantities and see whether, you see something sign changing when you go from single to multiple equilibrium regime. Now, there's quite a derivation, but you can actually look at the net, say, freshwater export or import by the AMOC in the Atlantic basin. And what this quantity means is that if sigma is positive, then this AMOC exports salt net in the Atlantic basin. And when the sigma is negative, it exports fresh water. And this is in this bifurcation analysis of this, say, full three-dimensional ocean model, global ocean model, you see that this boundary is exactly characterized by sign switch. Now, you have to be able to explain that physically, of course. And the explanation is sort of an integral version of this salt advection feedback. So it says that suppose you have an AMOC, which is just northern sinking, you put fresh water into the North Atlantic, then it becomes fresher, and the AMOC will decrease. Now, if it exports fresh water, then it exports less fresh water if it decreases, and so it becomes more fresh, and so that amplifies the original perturbation. And so you see that it's sort of an integral version of this, say, salt advection feedback. Now, how do models do in this respect? I mean, you could actually analyze models now and look at whether they have a net, if the AMOC in this model is net freshwater exporting or importing. And when you look at the earlier models, this is not in this diagram, but in the earlier models like CMAP2 and CMAP3, you find that all those models, they do have the wrong behavior. They all export salt, and they should export fresh water. And if you look at, say, the models here, well, let's first look at the observations. So these are reanalysis products, but there are also observations, explicit observations, and they all turn out, so these are the blue curves here, the blue crosses, the orange ones neglect those. It's sort of a correction which is built on there. But the blue ones, they indicate that the sigma here is negative, so that the fresh water, the AMOC would actually export fresh water. But most of the models here, you see these are the CMAP5 models, they actually transport salt, the AMOC transports salt out of the basin. And so this is not, the regime which is correct in those models. So there should be, enormous efforts to actually bias correct these models for this kind of feature. The reason is that the evaporation over the Atlantic in most of the models is too strong. So the Atlantic gets too salt. And the only thing what can happen is that the AMOC transports that out of the basin. And that's basically why it exports salt. So that's the first question. So based on observations, and we actually think, and based on this, say, indicator, which is this sigma, we think that the AMOC is actually in a multiple stable state. And so the next question is, what is the probability that it collapses before year 2100? Now, this is not an easy problem, because you'd have a, say, state here, which is state A, which is a present-day AMOC. And then you have a state which here is a collapse state. And you want to compute a say, probability that, and this is sketched below here, that the time you start in XA, so that is somewhere here in this neighborhood of A, and you want to know whether the arrival time of tau B, what the probability is that the arrival time tau B is smaller than some time tau. So this is the chosen, for instance, as the year 2100. Now you could do a naive Monte Carlo simulation, and that if the probability is very high, you might be with 100 ensemble members, you might actually, have a good chance. But if you're interested in very low probabilities, like 10⁻⁴, 10⁻⁵, then you need at least 10,000 to 100,000, say, ensemble members. And this is easy to do for a simple model, of course, for a small box model like Stommel. But if you look at, say, CMAP5 models, then it's, of course, impossible. So you'd have to devise other techniques to actually, say, do this, and people have addressed that. There's a lot of literature here in the chemical area where you look at, say, reaction kinetics, where different, say, molecules have to interact and to give a certain reaction. And so all these techniques which we use and which is used by others, they basically come from that area. Now, what is the, say, one of the techniques that you can use? There are several ones. There's sort of, there's actually two types of techniques you can use. One is you can use, go back to this slide here. You can actually try to compute, say, this trajectory, this path directly by looking at, say, path integrals, and then minimize the action over a certain path, and you can compute an instanton. That is one way to do it. This has actually been done already for Navier-Stokes equations, but it's quite some challenges for using that on ocean models. And the other one is more, say, ensemble based. And so here is one technique which is very popular at the moment, which is trajectory adaptive multi-level sampling. And the principle is you start at a point X here, and then what you want, you compute it, say, an ensemble. So this is the 3 trajectories you see here. And then what you do, you define a score function, and the score function tells you, how you're doing on the path to A and B, how close you are to B or how far you are from A. Of course, this is eventually, of course, the challenge, how to design that. But this is a score function. Now, you start in X, you run these ensembles, and then your score function will tell you, oh, one of those is not doing very well. It has the lowest score function. So you delete this trajectory. And then you start a new trajectory. You started from another trajectory, which has the same score function value as the maximum here. And realize this has different noise. So you get a different noise realization, and you get another trajectory. And in this way, you bias the ensemble, but you know exactly how you bias the ensemble. And from that, you can compute the transition probability. And this has to do with the number of trajectories discarded and the number which eventually arrive at B. So this is the technique. And well, of course, in the one of the things you try to do first is to look at, say, the box models, because there you have a low dimensional system, and so you would actually be able to check that with Monte Carlo whether your result is correct. As soon as you go up in the hierarchy here, and this is of course what we try to do at the moment, then it becomes more difficult to design score functions. Also, basically, you'd have to worry about how many ensembles you can run. So that is computationally very challenging. But let me show you some result here in the box models. So one of the box models, which looks a bit, awkward maybe at first, is a box model we designed, say, 8 years ago, to actually connect to this, say, quantity sigma, which basically is this freshwater export or import by the AMOC. And its structure is like this. So you see you have 5 boxes here. You have northern, tropical south, you have the southern and the deep boxes. And basically you have transport here. So this Qn would be the AMOC strength. So that is the northern sinking, say, volume transport. And then you see that you have a southern sinking state, which can vary in both directions. Qn can be full and can be 0, which would be a collapse of the AMOC. And then there's also here this pycnocline, which basically is the region of high density gradients in the deeper ocean. So that's also a dynamical variable. And then you see here this tropical south box is basically introduced because then you can look at this import of fresh water here in the region of say, the South Atlantic. You have also wind transport here. So this is wind-driven transports by the green arrows. And then you have this, say, freshwater fluxes, which we decompose into a symmetric part. So that would not break any symmetry. And then you have this asymmetric part here, which is basically the freshwater input, for instance, in the North Atlantic. And so by looking at this parameter EA, you basically can look at, how this, say, circulation, how it behaves. Now, this is also connecting a bit more to modern theories of the AMOC, where the wind-driven part in the Southern Ocean is important, apart from the, say, buoyancy-driven part. So how does the equations look like? Well, this is basically a typical box model. You see this theta is a Heaviside function where you basically control, say, the different transport, whether QS is positive or negative, the southern transport. And then this, you see also that the volumes of the boxes, they change. And that's because this depth of the thermocline is a dynamical variable. So you see that also here in there's an equation here for the thermocline depth. So it's all a bit more sophisticated than, the Stommel model, which is just based on well-mixed boxes and only heat exchange with the surface. Now, you see the parameters here. You see this EA here, which is this asymmetric component of the freshwater flux. This is our main parameter in there. And of course, we add noise to that after we look at the bifurcation diagrams. So here is the bifurcation diagram. Well, it's similar to what is the Stommel model. So again, you have Qn is here the strength of the AMOC, which you can tune to be in the observed range here. And then this is the freshwater input. And there you see that there's a region of multiple stable states here from, EA about 0.1 to 0.35. So again, you have two solenoid bifurcations bounding that. And we're going to look at eventually in the results on the transition probabilities, we're going to look at the value here, which is about 0.3. Now, if you look at the sigma here, then you see that sigma here also changes sign when you get into this multiple stable regime. You can compute it from the box model transport, and you can show in some limits analytically that actually this change happens. And you have a nice connection from this, say, simple box model to, the full dimensional ocean model, where you see the same behavior. Now you look at the stochastic part, and then stochastically you would also expect that it would be a bit more complicated. So here is a phase diagram where you see the behavior of this trajectory and also the different states. Here you see the Pickelkind depth. This is this depth of the, say, the larger gradients of the density in the ocean. And here you have a salinity difference. So this is actually the north-south salinity difference, which is important for, say, the AMOC strength. And then here you see a typical trajectory where you have here the on states, which are Qn is positive and Qs is positive. These are you have upwelling, which is positive. So these are the green region. And then you have the red region, which is to the left, where you see that you have off states where Qn is 0. So basically the AMOC is shut off in the north part, but still you see you have a circulation in the south, which is still positive. And then here you have these fully collapsed states where indeed the circulation has reversed. So this would be more like the Stommel state, where you have a collapsed state. And so the fixed points of this model are here. So this is the purple points here. Now, if you have noise here, you put it in the freshwater forcing. So this will be our mean freshwater forcing, and then we have a white noise and we have an amplitude F sigma here. And what you see is that the trajectories, they will, make a transition to the off state where the AMOC switches off, and then they go through this transition region and move to other regions, etc. So these will be typical trajectories of the stochastic system. And from here, you can actually compute transition probabilities. So here's the noise in the freshwater forcing here at the vertical axis. And then you have the AMOC indicator. So this is again this sigma value. You have it on the x-axis. And you see this is the colors are the transition probabilities. Now here you see that you can actually compute very low transition probabilities. So 10 to minus 8, 10 to minus 9. And that's because of this TMS algorithm. You don't need an enormous amount of ensemble members to actually get very low transition probabilities. So you get the total overview of this whole, say, two-parameter plane where you basically can look at transition probabilities. Now here you see typically to the right, you see two curves where you typically see the transition probability as function of the noise. So this is for MOV is for sigma is this case minus 0.1. So this black dotted along this line here. And then you see indeed that it's very low here. And then you see sharp increase at noise levels of 0.2, 0.3, getting to really probabilities near 1, right? When you go to very high noise here in this case. And you see also that is what you expect, that if your, say, MO sigma here, AMOC indicator becomes more negative, that actually the region over which you have, say, the transition probability high is larger. So you see here for the, say, MOV, so this is indicator 0.2, the other state here, you see that it basically is much quicker, it gets to sufficient, to substantial values, even for low noise. So this is somehow the picture you would expect based on, you know, the stability considerations. But you get a more quantitative estimate because you can actually, say, take this AMOC indicator from observations, and also you can make an estimate of the noise level. That is not trivial, but it's something you can do. And basically what you see is that this would be a sort of a most likely point that you actually have a substantial, you know, transition probabilities. This would be between, it's about 10% or so. Now, this is a very simple model, and you know, it's not something you'd like to say put a lot of say strength on in terms of you first have to check it, of course, in more complicated models. So that's something which we're going to do. But the simple model is such that you actually can connect this result here. You can connect it to observation because you have this AMOC indicator and the noise which you can both observe. So that is unlike many other box models where it's difficult to do that. So that brings me to the summary. I've shown you that the Atlantic Meridional overturning circulation is sensitive to freshwater perturbations and leading to a multiple equilibrium regime. And so I hope to show you that, you know, the salt advection feedback is something robust in the ocean. Basically, of course, there's other feedbacks, negative feedback, which could sort of weaken this. And we know those, several feedbacks in the atmosphere could actually do that. And so this is also a topic of future study, how to do that, how to look at the other effects of the atmospheric feedback. For instance, when the AMOC weakens, what you have also is that you have your freshwater flux changes pattern because the intertropical convergence zone shifts southwards. And so that will also affect the strength of the feedback. So this is something which you only can study well in a full-blown climate model. It's very difficult to devise, you know, very relatively simple atmospheric ocean models which give you the answer to this. Then the second point I showed you is that there is a regime indicator. This is also, of course, up to criticism because it's based only on ocean-only processes. Here also, you have to take into account the atmospheric feedbacks. Now, we've done that, and there's work on that. We also devised a correction to the original indicator, but those corrections are difficult to compute in climate models. And so here also work is needed to actually refine those regime indicators and be able to well, the best way is to, if you are able to, from observations, to actually detect whether you are in the multiple equilibrium machine, yes or no, that would be fantastic. So that's also something we focus on. Now, the last thing I showed you, this transition probabilities for this box model. And of course, I said that's too simple. So this is a lot of work which is currently being done to actually apply this TEMS algorithms to climate models. And what is crucial there is the construction of the score function. And the score functions, so we try that at the moment, doing that with machine learning to actually learn from the, say, the earlier trajectories, to learn the score function in this TEMS. And I would have liked to show you some of those results, but a bit too fresh to actually show in this talk. So that will maybe happen in the next talk. So thank you very much for your attention, and I'm really happy to answer questions.
Yes, thank you very much for this very instructive, clear talk. Questions, please. Yeah, Axel.
I don't hear anything.
Wait, it's coming.
Okay.
Hi, Henk. This is Axel.
Hi,
Good
Axel.
to see you.
Good to see you. Yeah. Hi.
So many years ago, I tried to work on noise-induced bifurcations or noise-induced transitions of the AMOC, and I had a really hard time figuring out what the noise amplitude of the freshwater actually is. So I'm curious, how did you obtain a realistic number? What's your recipe or strategy there?
Well, the strategy is to look just at observational products and look at different timescales. So how the noise will look like at different timescales. So it's very intermittent, right? This is the problem. But you can make an estimate, you know, if you allow noise on the interannual timescale, you can look, for instance, what the amplitude will be. You can make an estimate of that.
So it depends also on the time step of your model, because you have the central limit theory aspect of that. So this is accounted for in the case.
Yeah. But I agree, it's not an easy problem to do that, but you have to take a certain time scale on which you have the impression that the noise will influence, you know, this long-term circulation.
Okay, thanks, Henk.
Yeah.
Can you explain, you know, Axel is maybe the only expert here in the audience, except you. What are the time scales and which kind of noise is it?
You mean in terms of the freshwater flux?
Yeah.
Here we just take white noise. So this is very simplified approximation. If you look at the real noise property, that's very difficult, you know, to look at on the different timescales. But on the interannual timescales, white noise approximation not too bad.
Okay. Further questions? Maybe further questions? What about anthropogenic influence? What can we do? We have now this this COPs in Egypt, and what would you recommend the politicians?
You mean based on only the AMOC?
Yeah.
Well, you know, that is a very simple message. I mean, here also you would expect that when CO2 concentration increase in the atmosphere, that you would actually have, you know, both effects on the precipitation, which is very complicated, so it's not well known, but certainly on the input fresh water from Greenland ice melting, that is certainly something which will increase, as what you expect. And what we also see in observations, that is still very small contribution, but that's a contribution which may increase. And this is, of course, for the AMOC in terms of the, say, vulnerability, this is not, one should avoid that, right? So, yeah, the message is very simple as to immediately start, you know, much more effort in reducing emissions. Also for the AMOC. Now there are all kind of, people have suggested how to maybe control the AMOC, right? I mean, but those are, also solutions which are, basically practically very difficult. There's one, of course, very separate line, which is geoengineering. That if you put, say, stratospheric aerosols in the stratosphere, and people have done that in models, then what you see is that the AMOC recovers. So it will not, decrease as in most climate change scenarios, but it actually will recover. But also this is not, an optimal scenario.
Yeah. Further questions? Axel, one more, yeah, please.
The bifurcation diagram is, of course, very instructive, but the change over the next 100 years will be much faster than what you would expect from a system that is in equilibrium. So how relevant is really the connection between bifurcation diagrams and the weakening of the circulation, which may be just a forced non-autonomous or dynamic bifurcation problem rather than one where you really require multiple equilibria in the system? Yeah.
Now, this is, of course, an important point, which is now addressed by many groups, right? Looking at rate-induced transitions. Yeah, but still, even for the rate-induced transitions, it is important to know where the multiple equilibrium regime is, because that is something which will play a role also in these rate-induced transitions. So I see this, say, bifurcation diagram only as a sort of instructor, because I personally find it difficult to believe that, in this fully turbulent ocean flow, that we have, two solenoid bifurcations actually would bound its, say, multiple stable regime. I mean, of course, in reality, it's expected to be much more, say, complicated. But if there are two, attractors, then physically they might be distinguished by looking at, for instance, this, say, more macroscopic quantities like this export of fresh water by the AMOC. And so that is important to know, that kind of information. And I think we have still a long way to go to really look at, in the turbulent case, how you get transitions between those flows. I see it a little bit by the Rayleigh-Benjard problem. I mean, you have this heated layer from below, right? You have a bifurcation structure in the beginning, which is Pitchfork bifurcation. You get the rolled patterns. But if you look at the fully turbulent flow, then there are also transitions, which are called these wind reversals, where you see this transition between these turbulent flows, right? They occur, and they look like, solenoid bifurcations, but of course they're not. I see this is probably something similar also in the AMOC. But, you have to step by step work towards this type of analysis, and the rate of change and basically the small scale process will eventually matter.
Thanks.
Yeah. Okay,
Thanks.
we have also one question from Zoom participant. Can the parameter choices from your box model tell you in what regime you can see the AMOC collapse in more sophisticated models in a reasonable number of runs? Very long.
Yeah, that's a good question. I mean, basically what we do now is only, say, characterize it by this exporter and importer fresh water, which is sort of a derived quantity. Of course, you can look at how parameters in your box model, so that is the, say, for instance, parameters which influence the picnicline depth, you can see how that will influence this export of import of fresh water. So in the box model, you will be able to do that, but to connect that basically back to the sophisticated climate models is quite a task, because there's a lot of other processes which play a role, and so which might counteract the effects of parameters. So this is still a long way to go.
Okay, very good. Thank you very much, Henk. And we take your word that you will have another talk in 1-2 years to give us the other news. Thank you very much again.